Here we're going to talk about a topic that we didn't quite complete in class, and that's the electrolysis of water. So water can be both oxidized and reduced by electrolysis. Why is that? Well, if you look at, just going to give you the ink color here. If you look at H2O, the H in H2O is in the +1 oxidation state, and the O2 minus is in the -2 oxidation state. So water, the hydrogen in water can be reduced from the +1 oxidation state to 0, and the oxidation state, or the oxygen in water, can be oxidized from -2 to 0. So if you just do an electrolysis of water, you'll get hydrogen and oxygen. So O2 and H2. And here's the overall reaction. 2H2O goes to 2H2 plus O2. And let's investigate this in a little more detail. In particular, we want to know about cell voltages and how much voltage we'll actually have to put in an electrolytic cell in order to drive this reaction, electrolyze water, to make hydrogen gas and oxygen gas. All right, so let's write down the two half reactions. Let's first write down the what happens at the cathode. And remember, the cathode is where reduction occurs. And we said we're going to reduce the oxidation state of hydrogen from a +1 to a 0. So the half reaction for that is 2 electrons. And that will stick on the 2H2O, and that will give H2 plus OH2, put a 2 there, 2OH minus. Mistake, just try this again, plus 2OH minus. And then at the anode, and the anode, recall where the oxidation occurs, we're going to oxidize oxygen from a -2 state to a 0 state. So let's again start with, say, 2, H2O. We're going to oxidize that. We're going to make an O2. There, O2, that's oxygen gas. And we're going to have 4 H plus left over, and that's going to take 4 electrons. 2 electrons for each oxygen. And you have an O2 there. All right, so let's look up in TRO. We'll write down E0, and we'll use TRO's convention. Whenever we write E0, we'll be talking about the reduction potential. So there's a reduction potential. If you look up in the book, the standard, that 0 means standard, reduction potential of water, the hydrogen being reduced, is 0.82. And for the oxygen being oxidized, plus 1.23 volts. All right, those are standard. However, let's look at this in a little more detail. So here is a beaker of water, and we're going to put an electrode here. We're going to put an electrode here, and here's a battery. And what we want to do is to electrolyze water to make hydrogen and oxygen gas. What is the H plus concentration in here? Recall that the standard state, E0, if we use E0, we imply that the concentration of ions here, H plus, is 1 molar, and the concentration of OH is 1 molar. That's what that 0 means in E0. However, in pure water, and we're going to electrolyze pure water, the actual concentration of H plus is 1 times 10 to the -7th molar. And the actual concentration of OH minus is 1 times 10 to the -7th molar. So instead of standard state, we don't have standard state. How do we take that into account when we look at E cell? And in particular, how much voltage do we have to do to overcome the natural tendency to form water and drive it backwards and form H2 and O2? Well, we use the Nernst equation. Let's just write down, let's do the reduction first at the cathode. So we have 2 electrons and 2 water. Then we'll go to H2 and 2OH minus. Now the Nernst equation is the E of the cell will be E0, the standard state, and then we subtract off this quantity, RT over NF, times the natural log of Q, where this is a correction factor for the fact that we don't have standard state. Let's write down for this half reaction what Q is equal to. Q will be the pressure of H2. So this is a gas at standard state, so we have to use pressure. And it will be the concentration in molar of OH. And this will be squared. There's a 2 there, so we're going to square that 2. Let's assume that the pressure of H2 is 1 atmosphere. That's at standard state, even though the OH concentration is not. So if the pressure of H2 is 1 atmosphere. So remember, we just put the numbers in here, put 1 atmosphere, put 1 in there, we get OH, and that is squared. All right, so let's actually calculate this for the reduction. So E will be E0. Remember, we looked up in the, well, let's go back to this slide here. E0 for the reduction minus 0.82. That's what E0 is. That's in volts. Remember in class, RT over NF at 25 degrees, which is the standard state, is 0.02569 volts divided by N. N here is 2 electrons, so you divide this by 2, times the natural log of the OH concentration squared. We said for pure water, the OH concentration is 1 times 10 to the minus 7th molar, and we're going to square that. So this comes out to be 0.82. Do this calculation here. It's minus, it's a number less than 1, so this will be a minus, negative quantity here, so it's a minus of a minus. 0.414. So the actual cell, there's a correction for the fact that it's not a standard state. The actual cell voltage will be minus 0.41 volts. That's what that is for the reduction. All right, let's do the same thing for the oxidation. The oxidation occurring at the anode, remember that was 2 H2O. This goes to O2 plus 4 H plus let's see, 4 electrons, right? 4 electrons. And we said E0 for this. Again, that's 0 using Troll's convention. E0 means for reduction. The actual half cell potential when we reverse it will be the negative, but just let's go ahead with Troll. That reduction, that will be 1.23. Just look that up, volts in a table. Let's use a Nernst equation for this. E is equal to E0 minus, don't forget that minus, RT over NF times the natural log of Q. What is Q? Well, Q in this case is equal to the pressure of O2. We got products over reactants, and this water's not appearing because it's pure liquid, times H plus raised to the 4th power. And let's assume the pressure of O2, that's its standard state, 1 atmosphere. So this will just be the concentration of H plus, which we know to be 10 to the minus 7th, raised to the 4th, if the pressure of O2 is standard state 1 atmosphere. Okay, so let's go ahead and do that. Now this gets a little tricky here. E0 here was written as a reduction potential, just following Tro, but the actual E0 of this cell, because of this half reaction, because we reverse the sign of the direction of the reaction. Instead of a reduction, now it's written as an oxidation. Electrons are being produced. E0 is minus 1.23. Because in this Nernst equation, we want the actual E0 of whatever reaction or half reaction we're writing. Minus our T over F is 0.02567. N in this case, N is 4 electrons, times the natural log of the H plus concentration, which is 1 times 10 to the 7th raised to the 4th power. So this is minus 1.23 minus, and it'll be a negative number because this is, sorry, minus 7. This is less than 0. So it'll be minus 0.43. Minus a plus, so E0 for this half reaction is minus 0.80 volts. So for this particular half reaction, the where you've written it as an oxidation, the cell is there. If you write it as a reduction, in other words, if you reverse the direction of this reaction and write it as a reduction and taking into account the non-zero or non-standard state, E of this cell will be equal to plus 0.80. All right, so what have we done? We use a Nernst equation to correct for the fact that this occurs not at standard state. You get this. This is written as a reduction. And we've written this as an oxidation. We get this, or written as a reduction there. And remember, this occurs at the anode. So we have to sort of switch back, because that's the way TRO does it. I mean, you got to keep track of oxidation and reduction. So if you write it as a reduction, the E will be 0.80. If you write it as the oxidation, it'll be minus 0.80. And then for the cathode here, minus 0.41. So finally we get E cell will be E, as we said, of the cathode minus E of the anode. And using this equation, E are reduction voltages, because that's the formula. So these are E reduction voltages. So cathode, that's a reduction. Go back up here. The cathode minus 0.41. Okay. Minus 0.41 minus E of the anode. And E of the anode, remember, as a reduction is plus 0.80. All right. So the overall cell voltage here is, let's see if I do this in my head, probably not, so it's minus 0.39 volts. So note that's the minus sign. Okay, well, let's go back up here. Here's the reaction. Let's actually add this reaction up. All right, so we got 2 electrons here, we have 4 electrons here. So we're going to have to multiply this by 2 in order to get the number of electrons to cancel out. That's the general way you do it for a oxidation reduction potential, or oxidation reduction reaction. So we do that. We multiply this by 2. We get 4 electrons. So we have 4 H2O plus 2. That'll be 6 H2O. That goes to, we're multiplying this by 2. So that'll be 2 H2 plus O2 plus, we're multiplying this by 2, so that's 4 OH minus plus, there's 4 H plus. That 4 electrons will cancel out that 4 electrons, and we multiply by that. And this, in solution, will give you 4 H2O. So 4 H2O, that'll subtract off from the 6 So the net reaction is 2H2O goes to 2H2 plus O2. So there's the overall reaction. Okay, so let's see. Overall reaction. For this reaction, 2H2O goes to H2 plus O2. So 2 in front of there. The E for the cell is minus 0.39 volts. Okay? So that means that this reaction as written has a negative E cell, which means a positive delta G, and will not run as written. In fact, thermodynamically, you want to go the other way. However, we can make it go this way, the way it doesn't like to go from a delta G standpoint, by putting on a battery. So let's consider that now. Okay. Anything else? I think that's about it. All right. So here we go. Here's the beaker, and we have some water in here. And we didn't add any H plus or OH minus. The H plus concentration is 10 to the minus 7th. The OH concentration is 10 to the minus 7th. And here we have an electrode, just say a platinum electrode or some metal. And here we have a battery. Okay, so we're going to hook up here. And let's make this the plus terminal of the battery. And let's make this the minus terminal of the battery. So what's going to happen if you have enough voltage? In fact, if the voltage is over 0.39 volts, you can make this go in reverse. This now will be a positive. And you could generate hydrogen and oxygen at these two electrodes. Now, batteries. Let's talk a little bit about batteries. Here's a circuit. And the question is, which way do the electrons go? Well, actually, there are two ways to look at this. There's the way that us chemists will look at electron transport, and then there's a way that electrical engineers will look at. For us chemists, electrons are going to go from the negative down here. They flow from the negative. And so this is where, from a chemist's point of view, the electrons are flowing down here. You have electrons there. Reduction will occur here. And then over here, oxidation will occur. So oxidation occurs to the anode. So the anode is where it's connected to the plus terminal of the battery. Over here is a cathode. So for an electrolytic cell, the cathode is the electrode attached to the negative side of the battery. Now, if you're an electrical engineer, you're probably cringing at this. For an electrical engineer, if you have a circuit, here's a battery, and here we have some circuit, and let's make it a light or something, and we go back here. We'll make this the negative terminal of the battery, and this the positive terminal of the battery. If you're an electrical engineer, the circuit flows this way. It flows from the positive to the negative. If you're a chemist, it flows from the negative to the positive, because what we're looking at is electrons flowing. So the electrons flow down this way. So you can look at an electrical engineer circuit where it says the current flows this way, and this might be a light or something, as positive charges, the opposite of a negative charge, a positive charge going this way. So keep that in mind. For chemists, the negative part of the electrode, negative part of the battery is the cathode. Is where the electrons come down and reduce something. And the other terminal is the anode, the terminal connected to the positive. And again, this is for an electrolytic cell. Electrolytic cell, there's the anode. All right, so electrical engineer, if you take probably physics, even physics, it looks like conventionally the current flows from plus to a minus. But from a chemist's point of view, electrons flow from the minus to the plus. So you might ask, why was that? What happened? Well, back in the 1700s, this is essentially this is all I want to say about this. But let's talk about history. Back in the 1700s, Benjamin Franklin, yeah, the same Benjamin Franklin who did Poor Richard's Almanac, signed the, what did he sign, Declaration of Independence and all that other stuff. In fact, he probably wrote part of the Declaration of Independence along with Thomas Jefferson. He was also a scientist back then. This is in the 1700s. And no, I was not alive then. I actually was born after the 1700s. What he did, or actually before him, back in the really old days, if you took a glass rod, that's kind of interesting. So here's a glass rod. And you rubbed that glass rod with silk. All right, so you would induce a charge in the glass rod. If you took a rod of amber resin, and you rub with wool, you'll also get a charge. And it turns out, this is an amber rod, that the charges you get are opposite charges. So what, back in the old days, they had what's called a Leyden jar. In a Leyden jar, you would have on the outside of the jar some sort of metal. And on the inside, you'd also line the inside of the jar with some metal. And then you'd put some water here. And then out here, you would have sticking out some sort of metal conductor. So if you take the glass rod and touch it to this metal conductor, you could charge up this Leyden jar. And if you took the amber rod and touched it to the metal protrusion here, you can also get a charge. And what you find is that the if you have two Leyden jars, let's see, here's another Leyden jar here. Here's some water. We got the metal on the outside, metal on the inside. Okay, seal it up here. So if you touch, you rub this glass rod with silk and touch it here, and rub this amber rod with wool and touch it here, then you would get a spark, or you could get a spark going from one to another. So what Franklin was thinking is, okay, in one place you have an excess of something. He didn't know about electrons. They weren't discovered till like late 1800s, early 1900s. But he said you had an excess of something, and that something went from one place to another. And he arbitrarily said, all right, the one that I rubbed with a glass rod, we'll call this positive. Right? And the one we rubbed with the amber rod that we rubbed with a wool, we'll call this negative. So the positive had an excess of this whatever it was that was flowing, and the negative had a deficit of whatever was flowing. And what was flowing was, we know as electrons, but so the negative means a deficit of what was flowing. The positive means an excess of what was flowing. So Franklin said it went from positive to negative. But in fact, what we know is a negative now is electrons, and so the electrons are actually going the opposite way that Franklin originally defined it. All right, so that's why where Franklin defined it, all right, so you go from a positive to a negative. That's what's used in electric circuit diagrams. Okay, that's the way the current flows, or whatever it's flowing is flowing that way, because Franklin defined it back in the 1700s. We as chemists know that, in fact, it's electrons that are flowing, and they're from the negative part. We're going to call the electrons negatively charged. So, in fact, it goes the other way. So that's why for an electrolytic cell and chemists, we're getting electrons or current flowing one way, whereas an electrical engineer, using Franklin's definition of positive and negative, gets current is flowing the other way. Little historical note. Okay, that's it. Thanks.